All right, so increasing and decreasing. Have we ever used these words before?
Yes.
Doesn't want to click on the pen. This is a new thing. Okay, there we go. Yeah, we have, right? I mean, or have you ever... Goodness, just click on the red. Well, we may be writing them in black. That's okay. So we've talked about increasing and decreasing, but we've mostly just used it kind of in a pretty informal setting. All right. So I'm going to relate it to something we have talked about, and we're going to talk about more, which is relative extrema. Okay. So if you look at this picture, first of all, go ahead and draw little arrows at the end there. Can you locate the relative extrema? Okay, so like right here, what is that? A relative min. It also ends up being a absolute min, and same thing over here. But that doesn't always happen, where the relative is the same as the absolute. We can see up here, that is a relative max that is not the absolute max. Right, relative extrema will not be at an endpoint. Over here on this picture, first of all, let's just go ahead and draw in these asymptotes. And notice I'm not even really paying attention to the function. We're going to get to where, when we're not given a graph, how do we do this? But for right now, I just want to focus on, given the graph, how do we do this? Okay, I see relative extrema there and there. And again, these have little arrows at the end. So we can go ahead and put all that in to help us a little bit. So we have a relative max, or sorry, nope. Now it's going to be tough to erase. Here we go. This does not want to work with me today. So we have a relative min, and then over here we have a relative max. By the way, what do you notice the derivative is at all of those relative extrema? 0. Okay, that's going to be important for where we go with this next. Okay, so those relative maxes and mins are going to break up the increasing and decreasing intervals. Okay, so if we look at this, we can see that sometimes the graph is decreasing, then it's increasing, then decreasing, then increasing. And all of these relative extrema, those are kind of like the places where it stops doing one thing and starts doing something else. So increasing would happen here, and then in this piece as well. We can see that. What do you notice about the slope of that?
It's positive.
The slope is positive. Good. That's going to be important a little bit too. So when you write out the interval, I'm only writing the x values. So you're not writing from this point to this point. You're just saying from x equals -1 to x equals 0, f of x is increasing. And then since I have another piece, and I have some skipping, I'm going to put a u for union, and then that's going to go 1, 2, and since it keeps going, we would write infinity. Now notice my use of parentheses here. You already know that you need to use parentheses around infinity. But some of you might be thinking, well, maybe we should have brackets here. So hold that thought if you're thinking that. I'm going to explain why I'm using parentheses and not brackets in a minute. Okay, what about decreasing? What would those intervals be? Negative infinity to -1. And then from this max to this min, 0 to 1. Okay, so the interval is just the x value. Okay, so you go ahead and try 2 on your own. Okay, go ahead and compare your answer to mine, and I haven't finished my decreasing because I have a question. So from -2, from this little relative max through the asymptote, the graph is decreasing. F of x is decreasing. And f of x is decreasing on the other side of the asymptote. So can I just go -2, comma 0? What is the graph decreasing through the asymptote? No, nothing's happening at the asymptote. We have to make sure we skip it, which you might have done or you might have not done. And looking at a graph, I think that's pretty obvious. Like once I pointed out, when we're doing these and we're not given the graph and we're only given the equation, that's going to be the harder part to a problem like this. We'll work our way up to that. All right, now a definition for increasing and decreasing. This is real technical, but let me kind of just put it in easy words. A function is increasing if you have 2 points and the second point is higher than the first point. That's increasing. Vice versa for decreasing. However, we are going to put some calculus to this, and this is going to be how we talk about increasing and decreasing from now on. So a derivative of a function that is increasing. Okay, remember derivative? It's just like slope. Okay, so you guys already told me that's positive. So real quick, before we fill in the rest of those blanks, I want to go back to the first problem. At the relative min or the relative max, is the derivative positive? Or what is the derivative? 0. It's not positive. It's 0. That's why you cannot include those points. Now the AP test actually does take brackets. It accepts it. Most college professors are going to want you to put parentheses, and I'm going to use parentheses. And the reason the AP test takes it, because if you just go strictly by this definition, it kind of gets a little weird. But we're going to stick to the calculus definition. All right, so then what would the next blank be? The derivative of a function that is decreasing will always be negative. And we know a lot about derivatives, so we're going to stick with what we know. Derivative of a constant function. This would be like a horizontal line. 0. A function that changes from increasing to decreasing or vice versa, that happens at what? Where did we see that it changed? Relative extrema. And so before, we really weren't able to, we just were saying things like possible relative extrema. Now with this new information, we can actually say for sure where a relative max or min happens. This whole monotonic thing, we're not going to do a whole lot with this, but I want you to be familiar with this word. It might come up in a future class, and I want you to be educated. So a line like that would be monotonic, always increasing. We could have a curve that's increasing. You just have to be careful that you're not going flat and not ever for sure decreasing. So also monotonic would be something that's only decreasing. And again, you could have a curve to it, but you got to be careful that there's no places where the derivative is 0. And that's what monotonic means. Okay. So here we get a theorem, theorem 3.5, and we have a test. Okay, it's pretty much what we just said, but this is going to help us for problems like 3 where we're not given a graph. We're just given an f of x. So here's pretty much what happens. By the way, this is one of those theorems that doesn't have a special name, so we're not going to refer back to it. All right, it's just theorem 3.5. But notice the conditions. F has to be continuous, closed interval, differentiable. That's all. It's all the same stuff that we've been talking about. So number 1 says if f prime is greater than 0, or you could put a plus sign there, if f prime is positive, then f is increasing. This is kind of like the converse of what we just said. Or the inverse? No, converse. All right. 2 says if f prime is negative, or less than 0, then f would be decreasing. And if f prime is 0, then f is constant. So let's apply it to this problem. So no matter what we're doing, increasing, decreasing, we have to find the derivative. That's pretty much always going to be the first step. And so this is a pretty easy one to start off with. It definitely can get more difficult as the derivatives get messier. But we'll start off with an easy one. 3x squared minus 3x. So you want to know your critical numbers, just like how we did before. That would be where f prime is 0 or undefined. Is 3x squared minus 3x undefined anywhere? Nope. It is equal to, we can set it equal to 0. And now you got to solve this equation. And this is the part where some problems get really difficult, is solving this equation. Here, though, we're just going to factor. Factor out the 3x. What's left is an x minus 1. And when you factor like that, you can set each part equal to 0. And I'm going through this part quickly because we've already done it several times. These are our critical numbers. These are our possible relative maxes and mins. Okay, x equals 0 could be a relative max, it could be a relative min, it could be neither. Here's how we're going to do the next part of this problem. Okay, first we're going to draw a number line. So this is the new stuff for today. We haven't done this yet. And on the left, I want you to write negative infinity, and on the right, I want you to write infinity, and I want you to put your two critical numbers on the number line, and you really need to be careful and make sure that they are in the correct order. That's easy with 0 and 1. When we start getting negatives and fractions, you have to be careful about that. They have to be in the right order. Okay, so 0 and 1 are the places on a graph, okay, you don't have to write this down, but where it could change from increasing to decreasing and so on. And they're the only places where that could happen. Okay? So, what this means is actually good news, because what it means is whatever's happening over here in this section of the graph, to the left of 0, whatever happens at -1, something similar happens at -2 and at -3. By similar, I mean what's happening with the derivative. So you can take any number you want to the left of 0, say -1, okay? And we're going to plug -1 into the derivative. My suggestion, strong suggestion, would be to plug it into the factored form of the derivative. I don't really care what f prime of -1 equals exactly, but I want to know, is f prime positive or negative? That's what I want to figure out right here. Okay, so if I plug in a number, say -1, 3 times -1 is -3, and -1 minus 1 is -2. So what's a negative times a negative? Positive. So if f prime is positive, then what does that tell us about f? It's increasing. So what we're going to do is we're going to write this up here. So I want you to write an f above the number line, and I want you to draw like an arrow that looks like increasing. And you could also write the word increasing if you wanted to. And this would work with any number to the left of 0. Any number, if you plugged it in, you would get a negative, or negative times a negative, or a positive result, and therefore f would be increasing. Okay? If you take a number and you plug it in for x and you get 0, that means you missed a critical number. That's why we find the critical numbers first. Okay, so that's that section. Now we got to look at the section between 0 and 1. It is possible to have two pluses sitting right next to each other. So we have to test every section. It's possible for it to switch and go negative. So pick a number, any number between 0 and 1. Probably 1/2 or 0.5 is what most people would pick. Now again, you don't need to crunch the numbers. You just need to think, if I plugged in 1/2, like 3 times a half, that's a positive. A half minus 1, that's a negative. Positive times a negative, negative, and that would mean that F is decreasing. And this would work with any number between 0 and 1. Okay, pick a number greater than 1. 2. So if I plug in 2, 3 times 2, positive, 2 minus 1, positive, multiply them together, that's positive. And so up here for F, we're going to draw an increasing arrow. So this is what's called a sign chart. Sign, S-I-G-N, like pluses and minuses signs. And it kind of makes it easy for us to organize our work. Now we need to write our answer. Okay, so we have F is increasing on what interval? Negative infinity to 0. Union that with 1 to infinity. Right? Because, now this is the part you may not like. We have to write y. How do we know this? Because F prime is what? Positive. Likewise, F is decreasing on 0 to 1 because F prime is negative. And that's all you have to do. So finding the derivative and solving for those critical numbers really is the hardest part of these problems. Okay, now how does this relate back to relative maxes and mins? Okay, well, if you have a really nice sign chart, especially if you've drawn these arrows, you can kind of figure out what the graph is doing. F of x is increasing, and at 0 it levels out, and then it's decreasing. So what's happening at x equals 0? A relative max. And you can kind of almost see it right here. It's a relative max. It's going to go up, it's going to top out. I don't know if it's absolute max. That's not what we're talking about here, though. That's what we would have to do, you know, where we plug it back into the original. I'm just saying in this area, x equals 0 yields the highest point just in this area. Okay, so that's what theorem 3.6 is talking about. And it says the first derivative test because we will have something called the second derivative test. Okay, we'll worry about that later. We'll talk about it before the week's over. It's not really that hard, but you may be wondering, like, why are we saying first? There is a second. So if we have a critical number, okay, and f prime changes from negative to positive, then that's a relative min. So we can see that happening here at x equals 1. And then at x equals 0, the other thing is happening. So this is how we're going to write out those answers. We're going to say f has a relative max at x equals 0. I don't care about the y value with these. Just where is it happening? At x equals 0, because f prime changes from what to what. And you don't have to have the rule memorized. Just go back up and look at your sign chart from positive to negative. Now, I did a lot of abbreviations here. This is about as little as you can get away with and get full credit. You really can't write less than this. That whole because statement, that's going to be something we just do on every problem. So what would the corresponding relative min statement be? F has a relative min at x equals 1 because f prime changes from negative to positive. So notice that for increasing, decreasing, relative max, and relative min, all of those because statements started with f prime and had to do with positives and negatives. Okay, one last thing that I want to kind of leave us with is we just did a problem where we had 0 and 1, and one of those was a max and one was a min. do you think it could be possible to where 0 wouldn't be either? Like, what would have to happen with these signs for 0 to not give us a max or a min? It would be plus plus or minus minus. Do you know what that would look like on a graph? Where the graph is increasing, maybe? Like plus plus would be increasing, leveling off, but instead of changing directions, going up again. A saddle point. Which I kind of have thrown that out a little bit. Those are more rare. I will tell you, a lot of times it just flips back and forth like this. But not every time. So we'll get to that part tomorrow. Like that.